The electric field will be discussed first. For the electric field, we will start with Coulombs Law, which describes the force between two charges, Q1 and Q2, times the Coulombs constant, and please note the absolute values here. We're just dealing with the magnitude of the force, divided by the distance between the two charges squared. This gives the force between the two charges. Similar to the gravitational force, these two charges do not have to be touching each other to feel a force. They can be at a distance from each other. We call this action at a distance, and it's best understood by assuming that each charge has a field surrounding it, and it is this field that affects other charges that come near it, and we will call this the electric field. First, we'll deal with the electric field due to only one charge. We're going to take Coulomb's law and just change it a little bit. We're going to assume that one charge, this capital Q here, is very large. And that's the charge we're going to try and find the electric field around. We're going to take Coulomb's law and change Q2 to just little q. And this means that Q is very tiny compared to big Q. And the reason will become apparent because we don't want to worry about any electric field created by this small charge. The distance will simplify it from r sub 1, 2 to just r. We will take away the absolute value signs and we'll emphasize the vector nature of the force. The electric force, of course, has magnitude and direction. Okay, so we have Coulomb's law here, where we have Q is this large charge that we're trying to find the electric field about. Q is a small positive test charge. I didn't mention positive, but it is a positive charge, and we do that for convention. It will help us keep the direction of this field straight. R, of course, is the distance between large Q and this little tiny test charge. So the first thing we're going to do is get rid of the test charge. We will divide both sides of the equation by Q, and that will leave this side as KQ over R squared. And then we'll define the force divided by a small charge as our electric field. So the electric field is equal to KQ over R squared. This will show both the magnitude and direction of the force on any charge due to big Q. And the way we get that force is we just take the force will be equal to any charge that comes near big Q and times it by the electric field. And notice I'm emphasizing the vector notation over here. Q, or the large charge, creates the electric field. The size of charge Q and the distance to the point will determine how strong the electric field is at that point. The electric field is measured in newtons per coulomb. Later on we'll show how it's also volts per meter, but for now let's stick with this. And a good way of remembering that is once you have the definition here, force over Q for the electric field, the units of force are newtons, the units of Q are coulombs, so here you go, newtons per coulomb. Now the electric field, you can't see it. But we will represent it as a group of lines that show its direction and strength. And the reason we do it is so we can understand it. We don't always have to see something for us to make sense of it. And that direction, those force lines, will show the directions of the force that it would exert on a positive charge. So these imaginary electric field lines always originate on positive charges and terminate on negative charges. It's always better to visualize things. I said on the last slide, I talked about what electric field lines, here they are. See these arrows? I have an isolated positive charge. This would be our big Q. And I want to describe the electric field surrounding it. Well, the field lines point radially away from it in all directions. And now this is just a two-dimensional model. If you were to look at this in 3 dimensions, it would look like a beach ball with a bunch of spikes out of it, or a hedgehog, or a porcupine. So these lines go in all 3 dimensions, but again, this is a piece of paper, so it's a little hard to show that. They are all pointing away, which means if I take any other charge, a small positive test charge, or even a bigger test charge, or just a really, really large charge, it will still be pushed away because likes repel. So the direction that this charge would move is radial away from Q. This one would move that way also. So all the electric field lines are pointing outwards from the positive charge. Now let's say our Q, our big Q, happens to be negative like we have over here. This also creates an electric field, But in this case, any positive charge I put outside of it will be attracted to it. So you can see the arrows here. They're pointing in towards the negative charge because any positive charge I put will be attracted in that direction, and you can see how that lines up with the electric field lines. Our definition of the electric field said it was equal to E is equal to KQ over R squared. So it's proportional to 1 over R squared. So the strength of this field will decrease as the distance increases. A way of visualizing that is by the density of the electric field lines. If I take an area of space, let's say it's around this large, you can see we have one electric field line going through it. If I take kind of the same area, and this is a little tricky, but let's draw it here, you can see I've got 1, 2, 3, 4, well, it's kind of cheating, actually it just has 3 lines. But there are 3 lines covered by this area. That tells you that the electric field is much stronger closer to the charge. So wherever the lines are more dense, that will be the stronger electric field. There's a great simulator here. If you click on this, it will take you to it. You can put various charges and various arrangements and see what the electric field looks like. Slides like this help put a human face on the physics. Michael Faraday is the person whom the electric field is attributed to. He was born in London in 1791, came from a poor family. He started out as a bookseller and binder, and we still have books around. Those are those things made out of paper that you can read and find information on. And he started attending local lectures on philosophical and scientific topics. Fortunately, somebody took notice of him, brought him into the Institute, and then he made numerous contributions to physics and chemistry. And it'd be great to look him up and see what else he has done for those 2 topics.